Hello there and welcome back to another video. Today we're going to be talking about mass and energy balances, and specifically we're going to be looking at a situation where we have a tank of water and we're going to say it's well stirred, and we have flow rate coming in and another flow rate coming out. So, for this situation, we have a temperature of this water. So, let's call this temperature of the water in the tank, and that is equal to 300 kelvins. So we've got that temperature, but then in this flow in, the temperature of the water is equal to 320 kelvins. And so there's going to be a change in temperature as over time, and we want to see how that change in temperature over time relates to the change in this height of the water, because we're putting water in and then water's flowing out, so the water is going to rise or it could fall. We don't know. We want to find out. So we've got this height, and we want to know how the change in height changes with time and the change or the temperature changes with time. And so we're going to do this by looking at the mass balance and energy balance. So we're going to focus on finding the height with respect to time first. So we want to find the mass balance equation. So we know that the change in the mass of the system is equal to the change of the mass going in minus the change in the mass going out. And so you might think to yourself, okay, well, we want the height. How are we going to find the height? But we see that we have a mass, and we know that mass is equal to the density times the volume. And we see that this tank, it's a spherical tank, and it has an area, cross-sectional area here. So, well, it's not spherical, it's a tank, so it has cross-sectional area here. So we know that, and we want to know how the height changes. So we know that the change in the mass is really just the change in the density times the area, cross-sectional area, times the height. And then we want to know that with respect to time. And so we know that the change in the mass going in is just equal to the flow rate going in times the density minus this flow rate going out. And we know, I forgot to put it down, that the flow rate going out is equal to alpha times the height to the 1/2 power. So we know that. So we know that Q out times the density. So we know that the density times the height, I forgot alpha. Density times alpha times height to the 1/2 power. And so we notice that the density of the tank here is just water, and that's a constant. And we also recognize that the area is a constant as well. And so they're not changing, so that means we can pull them out of this derivative. And we notice that we've got the densities on both sides here. So when we pull that out, divide it over, these are going to cancel out. And we're just going to go ahead and we want to isolate the change in height with respect to time. So we're going to divide by the area as well. So that leaves us with the change in height with respect to the time is equal to the flow rate in minus the alpha times the height to the 1/2 power, which is the flow rate out, divided by the area. Alright, so that gives us our equation for the change in height with respect to time. So we also want to know how the temperature changes with respect to time. And we're going to do this with an energy balance. But in this situation, we don't need the whole energy balance equation. It's big and long, and we want to save some time here. So we know that the potential and kinetic energy are going to be negligible for this system. So that is going to let us write the system, or write the equation and shorten it to the change in mass times the internal energy of the system with respect to time is going to be equal to the enthalpy going in, so we're going to call that H in, lowercase h for enthalpy, times the change in the mass of the system going in with respect to time, minus the enthalpy going out times the change in the mass of the mass going out with respect to time. Alright, so let's go ahead and plug in what we know. It's just going to be just like we did over here, where we know that the change in mass, the mass is just the density times the area times the height. So we're just going to go ahead and do that over here. But we need to add in this internal energy of the system this time. And so we know that with respect to time. And going to go ahead and the enthalpy in, we're going to go ahead and change the change in mass in. We know that that is the Q in times the density minus the enthalpy out, and then times the density times the Q out, which is just alpha, times h to the 1/2. And so we're going to do exactly what we did over here again. Very similar systems, we just need this internal energy here. So we're going to pull out the density and the area and then divide by both of those. So I'm going to go ahead and do that. So we're just left with delta, or the change in h times the mass, or the internal energy of the system with respect to time. And that is going to be equal to the enthalpy in times the flow rate in minus the enthalpy out times alpha times the height to the 1/2 power, and this is going to be divided by the area. So now we need to recognize that we don't have temperature anywhere in this equation, but we have the enthalpy and the internal energy of the system. And we know that the change in enthalpy is equal to the specific heat times the change in temperature. And we also know that the change in internal energy is equal to the heat capacity times the change in temperature. And so if we think about this as the enthalpy is equal to specific heat times a temperature minus some other temperature, call that the reference temperature, that in this situation we can just ignore this reference temperature. So we just have this specific heat times the temperature, and we can go ahead and plug that in for the enthalpy, and we can do the same thing with our heat capacity. It's equal to the same temperature reference here, but we're going to ignore that in this situation. So we can go in and plug this in for our, I don't like that T, sorry. Just plug in our variables now so we can further simplify. So we know that the specific heat times the temperature times Q in, which is the flow rate in, minus CV times the temperature times alpha times the height to the 1/2 power divided by the area. And so I'm just going to go ahead and further simplify this. We're going to be able to pull out this CP because it's constant. It's not going to change. This temperature is going to change with time. but this specific heat isn't going, or sorry, heat capacity isn't going to change with time. So we're going to be able to pull that out. So I'm just going to go ahead and pull that out here, and we are left with that. And we're going to do the same thing here. We're just going to pull out the specific heat and then do the temperature times the flow rate in, it's an N, minus the temperature times the flow rate out, which is alpha, times height to the 1/2 power. And all of this is over the cross-sectional area. All right, so we also need to recognize that for our liquid in our system, the difference between the specific heat and the heat capacity is going to be negligible. So we're going to just set them equal to each other, and that will allow us to cancel these two out. And so we're left with this. And so now we're going to apply the chain rule. So we're going to be left with the temperature times the change in height with respect to time, plus the change, plus the height times the change in temperature with respect to time. And that is going to be equal to temperature times the flow rate in minus the temperature times alpha h to the 1/2 over the area. And so we want to solve for the change in temperature with respect to time. So we're going to move this, subtract that over, and then divide by the height. So let's do that and end up with our final equation. So we've got the temperature times the flow rate in times, or minus the temperature times the flow rate out, which is alpha to the times h to the 1/2 power, or the cross-sectional area, minus the temperature. Ooh, that was ugly. Minus the temperature times the change in height with respect to time, and all of this over the height. And so now that we have this final equation, we are going to go ahead and use Python to generate us a plot that'll let us look at how the height changes with respect to time and how the temperature changes with respect to time. So I'm going to go do that now. All right, so now we're over on Google Colab, so we can make our plots in Python. So you see I already have some code written out, just some time-saving stuff. I'm going to be using NumPy for some of the math and the arrays, so imported that, and then I've got our differential equation solver, and then just our subplots. And as I like to do them, I like to make them a dark background. And then here are our initial equations, or initial conditions for this situation over here. Cross-sectional area is 1 meter squared. We have an initial height of 1 meter, initial temperature 300 kelvins. Temperature going in is 320 kelvins. The mass flow rate in is 1 meters cubed per second, and then alpha is 0.4. And then we're looking at this for a time of 100 seconds. So the first thing we're going to need to do is define our differential equation. So I'm just going to call this diff1, and we need two parts to this. We need it going through time, and then this arbitrary letter k. And so what k is going to let us do is it is going to be an array. So it is going to contain, it's going to contain our height and our temperature and how that changes. So I'm going to set that equal to k. And so now what we need to do is see how our, just set in our equations. So we've got dH, and we've got that equal to Qn minus alpha times our height to the 1/2 power. And I'm going to go ahead and add in the parentheses we need. And this is all divided by the area. All right. So, we want this by the area. All right, now we want to type in our equation for the change in temperature. So dt, change in temperature, this one's a little bit more tricky, so it's going to need way more parentheses. So we've got the temperature going in times the Q going in, the mass flow rate in. We've got all of that minus the temperature times alpha times the height times the height to the 1/2 power. And this is all divided by the area. And then we've got this temperature times the change in height, so dH, and then all of this is divided by the height. And then we need to return dH and dt, but we need to do this as an array. So we've got numpy array, I could spell, and then we need dH and dt, dH and dt. All right, what did we miss? All right, so I'm going to try adding in a few more parentheses to see if that helps solve this problem we have here. I want to make sure these are all connected. There we go. And then I want to make sure we've got this set up properly. And let me just go through and check my parentheses. Okay. And then divided by A. Okay. All right. So all of our parentheses are there. Still getting an error. I'm gonna have to cut and jump back once I figure out my error. Alright, so I figured out the problem. I had it indented wrong, and the spacing was weird, and Python didn't like that. So I fixed that. Nothing else significantly changed it. Everything else is where it should be. So I'm going to go ahead and continue with what we were doing. So we want to go ahead and solve this differential equation, and we want to use our solve the initial value problem that we imported from SciPy. So we want to use solve IVP, and we want to do this for our diff1, first differential equation, and we need to do this for the time from 0 to our time variable, 0 second, or out of 100 seconds, Oh, I missed. This is supposed to be in brackets. 0 time in brackets, and then we want the and then we need a numpy array. Of h, the initial height, and the initial temperature. We need an array of that, and then we need our method, and the method we're going to use is called RALDEU. And then we need our dense output. That's not it. Output is equal to true. And then we want, true isn't defined. Need to capitalize the true. All right, so that's working. So now what we need to do is, because we're trying to plot this data, we need some time values that we can plot. So we want, just gonna make a new set of time values, and we're gonna set, they're gonna be linearly spaced values of time from 0 to our time variable, and we're gonna make 500 of them. Sounds like a good arbitrary number. Then what we're gonna need to do is we want to pass our two variables here through this function, and we want to do that with the time plot values. And now we can go ahead and plot the data. So we are going to make some figures. So figure 1 is going to be equal to make subplots. Make subplots. And then we want, we're going to want two graphs side by side. So we want our rows to be 1 and our columns to be 2. All right, so now we want to add the scatter plots. Add scatter, and we want to set our x value equal to the time plot. So we want our x-axis to be, and then we want our y-axis for the first graph to be equal to the height values. And then we want this to be at row. It'll just be row 1, because we only have one row. And we want this to be column 1. All right. And then we want to do another plot. We're going to add scatter. Want the same x value. Use for both. Time plot. And then we want our y value to be equal to the temperature. And then we want this to be the first row. We want this to be column 2. And there we have our temperature plots. We can see they both look pretty similar, and that's kind of what we expected to happen. Alright, so now I'm going to go back to the notebook, and we are going to derive a similar situation, but instead of a temperature going in and instead of a temperature going in and the temperature changing, we're going to analyze what would happen if the concentration were to be changing inside of the tank. Alright, so here we have our second situation. You can see it's very similar to our first situation, but instead of a temperature changing with time, we want to know about how the concentration changes with time, and then also still how the height changes with time. So we have some initial concentration of a liquid, and then we have another concentration coming in of a liquid, and then we have this Q out, so we have it flowing out as well. So the height is going to change with time, and the concentration is going to change with time. And you can see that I have this equation copied over from our first part, and this is because we still want to know how the height changes with respect to time, and this situation didn't involve temperature before, and so it will still hold for our case here with the concentration if we know that the density of the system is equal to the density in, which is equal to the density out. So if we just say the density of the concentrations of the liquid is the same throughout, then this equation still holds true. So now we want to know, how does the concentration change with time? And so we still know that we can do a mass balance. So we know that the change in the mass of our system is equal to the change in the mass going in minus the change in the mass going out. And all this is with respect to time. So we know this. And so we can make the next step is that we know the mass of the system is going to be equal to the height times the cross-sectional area times this initial concentration. So we know that the change in concentration times the height times the area divided by the change in time, that is going to be equal to the concentration coming in times Q in, and this is going to be subtracted by the concentration going out, but the concentration going out, because it's perfectly mixed, is just going to be the concentration of the system. So that's just going to be regular C, not C in, times the Q out, the mass rate, or the mass flow out, which is alpha times the height to the 1/2 power. Alright, and so we know that this cross-sectional area is constant, so we're going to be able to pull that out and then divide. So I'm just going to do that here in this step just to save a little bit of time. So there we go. So now we need to apply the chain rule because we want the change in concentration with respect to time. So we know that concentration times the change in height times divided by the change in time plus the height times the change in concentration over the change in time is equal to flow rate, or the concentration coming in times the mass flow in minus concentration of the system times alpha height to the 1/2 power divided by the area. And so we want this quantity here, so we are going to subtract across and then divide by H. Very similar to what we did with the temperature, just instead of a T we have a C, so it should look pretty familiar, all the steps that I'm doing. So subtract that over, so we end up with all of this staying the same, divided by cross-sectional area minus change in height, change in temperature, all of this divided by the height. All right, so here is our change in concentration with respect to time. So now we can just go ahead and plug it in to Python, and because our equations are so similar, we're not going to have to do a whole lot of coding. We're just going to be able to change what we already did and just go ahead and change the temperatures to concentrations. All right, so we are back in Colaboratory to code up the second situation. And you can see I opened up into the same notebook as before, and that's because these situations are very similar to the situation in part 1. So we're going to be able to use a lot of the code, and by a lot I mean like 90+%. So all I need to do is add in the new initial conditions, and that is the concentration initially is going to be 0.1, and then the concentration going in, that is equal to 1. And so if we update that, then we have our initial conditions, and I guess I should be consistent here and put in the units, and that's kilograms per meter cubed for both of them. All right, so what we're going to do is, I don't want to ruin what code we've already done, so I'm just going to go ahead and copy and paste these, but we're going to be changing, just changing it up. So we're going to call this our differential equation 2, and we don't want any more temperature values. We want all our temperature values to be concentrations now, because as we see over here in our notebook, we have C's everywhere we had T's before, and that's pretty much the only difference. So I'm just going to go through and change all of our T's to C's. Temperature here, C there, one there, and one there. All right. Shift enter, go up here and copy over the next part. Go through and do the same thing. Solve the second differential equation for time. We don't want the temperature initial, we want the initial concentration. Then we don't want temperature anymore, we want concentration. So everything there is good. And then we just want to copy over our scatter plots, and we're going to call this figure 2, and instead of temperature we want the concentration. So now that we do that, we see our plots, and you can see that this change in height plot is the same for both. And then you can see that this second plot here, since it's concentration, it's going from 0 to 1, and here the temperature is going from 300, which was the initial temperature, to 320, or approaching 320, because that's the temperature of the water going in. So both of these graphs make sense, so we have our plots. Thanks for watching.